It's a great pleasure to introduce our speaker today, Yvon Verberne, University of Toronto. Her title is Symmetries of Surfaces.
All right. Thank you so much for having me. So for today's talk, what I want to do is I want to introduce the notion of surfaces, and in particular, what I mean when I say that I study the symmetries of a surface. As a spoiler, this ends up being a group. And what I want to do is I want to look at the history of this group, and I want to give you some idea of where my research fits into this really rich history. So when I say surface, what I mean is a two-dimensional manifold. So all of these objects that you see here, they're all hollow. So when I say that I'm studying a torus, or as we all like to call it, a donut, I'm not studying the dough of the donut, I'm only studying the glaze of a donut. So all of these objects are hollow. And then for these objects, we split them into two different categories. So for of these surfaces, the ones here, we call them finite type surfaces. They have a finite amount of topology, and so they have a finitely generated fundamental group. But then this object down here, I need you to put on your imagination, because there's an infinite amount of genus in one direction and an infinite amount of genus in the other direction. So this has an infinite amount of topology. And so the fundamental group here is infinitely generated. So we end up splitting these off into finite type and infinite type surfaces. And we'll mainly cover finite type today, but at the end, we'll go a little bit into infinite type surfaces. So the group that I like to study is called the mapping class group. This is the group of orientation preserving homeomorphisms up to homotopy. So a homotopy is when you can take a surface, and if I take two maps applied to the surface F and G, but I can take the surface after I've applied F and continuously deform it into G without breaking the surface, then F and G are in the same homotopy class. But if I need to break my surface after I've applied F in order to get to the surface after I applied G, they're in different homotopy classes. And we'll look at an example to kind of make that more concrete later. Another way to... Not always. Sometimes we have punctures. So one way to think about this is that this is the group of symmetries of a surface. So you have some of your classical symmetries. So here we see a rotation of order 5 on the surface of genus 6. We also have things that are reflections. We call them involutions. But then we also have more complicated symmetries, which have infinite order. And we'll get into some examples of those later. So the first thing I want to do is convince you that the study of mapping class groups is an interesting topic in and of its own right. So mapping class groups show up in many other areas of mathematics, but also beyond. So one of the examples is in algebraic geometry. So if you look at pi1 of moduli space, that's equal to the mapping class group. So there's a lot of questions about moduli spaces that you're actually able to learn and prove using results from mapping class groups. In complex dynamics, you can study complex polynomials using the mapping class group. For example, the twisted rabbit problem was recently solved using mapping class group techniques, which gives us an entirely new way to study complex dynamics. In topology, every single 3-manifold is able to come from a Heegard splitting. A Heegard splitting says that you have two handle bodies with boundary, and so these handle bodies are 3-manifolds. So the boundary is the surface. And then you're going to glue the boundaries together using an element of the mapping class group to get your whole 3-manifold. So one way to think about this is every single 3-manifold is able to come from an element of the mapping class group. We also see mapping class groups come up in the study of physics. So one example of this is fluid stirring. So when you're in industry, you need to mix fluids, and you have to mix them in complicated ways without ruining the thing that you're mixing. So overmixing can actually be detrimental in industry. But when you study mapping class groups, you study these maps that do a lot of mixing, but don't necessarily need to be, you don't need to do many rotations of it, so you don't risk breaking your product. And in fact, one of the projects that I'm going to talk about today was recently applied by a student that was in joint math and physics, where they studied fluid stirring of particularly punctured spheres. We also see mapping class groups come up in number theory. And the reason for this is that when you look at an element of the mapping class group, there's this value that's called a stretch factor, which tells you how much mixing is happening on the surface. But this number is also very heavily related in number theory. And so we can use number theory to help us understand these stretch factors significantly better. And finally, fortunately for us, people in analysis were able to solve the question of what the Poisson boundary of the mapping class group looks like. So it isn't just that we're applying to other places. We also have researchers from other fields help us to understand our group significantly better. So I told you that I have a group, but what's a group without a generating set? So one of the great results by Dane and Licorice is that you can generate the mapping class group using finitely many Dane twists. So let's define a Dane twist. We're going to do this by an example. Here's my torus, and I have two curves in the surface. I have my curve alpha here, and then I have my curve beta. And what I want to do is I want to twist my curve beta around the curve alpha. One way to picture this is first I'm going to cut open my surface along the curve alpha. So now notice I have a cylinder with two boundary components. And what I'm going to do is I'm going to grab hold of one of the boundary components, and I'm going to twist it by 360 degrees. When I've twisted it by 360 degrees, I'm going to glue the two boundary components back together. Notice that this curve here, this blue curve, is very different from this curve beta here. In fact, there is no way for me to continuously stretch or deform or twist the surface without breaking it to get from the curve on the right back to the curve on the left. That tells me that a Dane twist and the identity element are not homotopic. So this is in fact an element that's different in the mapping class group. So now that we know what a Dane twist is, Humphreys was able to give us the generating set that we use the most often. So the generating set that Humphreys described is the minimal generating set if you're going to generate the group using Dane twists. So in particular, you need two G+1 twists. And something I want you to notice is that if you take any of these curves and cut along it with a pair of scissors, your surface stays connected. So each of the curves in the Humphreys generating set is called a non-separating curve because the surface stays in one piece when you cut along it. Using this generating set, you're able to prove that the Abelianization of the mapping class group is trivial. And the proof that I'm going to show you is from Harrer. So a nice fact that we know in mapping class groups is that Dane twists around non-separating curves are all conjugate. So in the Abelianization, this means that each of these elements, because they're conjugate, they have to map to the same element H in the Abelianization. What you see here is a sphere with 4 boundary components, where I've labeled the boundary components by B1, B2, B3, and B4. On the inside of the sphere, I have 3 curves. I have X, Y, and then Z here goes around B2 and around B4. This is what we call a lantern. And this satisfies the lantern relation. So in particular, if you twist around the curve X and the curve Y and the curve Z, this is the same as twisting around the boundary component B1, then B2, then B3, and then B4. If I take a surface of genus at least 3, I'm always able to embed this lantern so that each of the curves in this lantern are non-separating curves. So the boundary curves are really easy to see that they're non-separating. But for instance, this curve Z here is a little bit harder to see, but trust me, that's still a non-separating curve. So I have the lantern relation, and all non-separating curves map to H. So now what I have is that H cubed is equal to H4, which means that each of these curves are trivial. But every single generator in the Humphreys generating set is also non-trivial. So they all map to H, which means every Dane twist in the Abelianization actually just maps to the identity. So my Abelianization here is trivial. So one of the first themes I want to cover today are the different types of mapping classes. So in particular, the Nielsen Thurston classification tells us that there's exactly 3 different types of mapping classes. So if you pick an element of the mapping class group, it has to be of one of 3 types. The first type are the periodic mapping classes. These are the mapping classes that have finite order. So your rotations, your involutions. And another way that we like to think about this is that every single curve on the surface will eventually map back to itself. On the other hand, we also have the Pseudo and ASAP mapping classes. These are as far away from periodic as you could possibly imagine. These are the mapping classes that mix the underlying surface in the most complicated way possible. Thurston was able to show that one definition of a Pseudo and ASAP mapping class is that there exists a value lambda greater than 1, and a pair of transverse foliations. There's the unstable foliation, which gets stretched by a factor of lambda, and the stable foliation, which gets contracted by a factor of lambda. And this value lambda is what we call the stretch factor. It tells you how much mixing is happening in your surface. So if we look at this image of my surface of genus 2, I've given us a schematic of a Pseudo and ASAP map. So I have two foliations. I have the red and the blue, and these are transverse on the surface. When you do a mapping class and you look at a little neighborhood of your surface, so U, and then you look at its image under the map, you're going to notice that they're stretching in one direction. So here we have stretching in the blue direction. So the blue is going to be my unstable foliation. And then we see contracting in the red direction. So that's going to be my unstable foliation. Like, does the surface? Yeah, so the homeomorphisms we do preserve all the topological properties of the surface, not area. I think it's still area preserving, because the amount of stretching that you do in one direction equals the amount of contraction you do in the other direction. And so it should be area preserving. Yeah, so you kind of just see that it's shearing. Does that make sense? Yeah, so it is area preserving. All right, and then here we see an example in R squared. We have two foliations. And if you apply the matrix 2, 1, 1, 1 to our vector xy, you end up seeing that these two foliations actually stay preserved under that map. And in fact, a matrix very similar to this one's going to come up later, because this actually does correspond to a Pseudo and ASAP mapping class. The final type of map that you can get in the mapping class group is called a reducible mapping class. So for a reducible mapping class, you're going to have a collection of disjoint curves on the surface. And you can imagine those curves as breaking up the surface into different pieces. Some of these pieces are going to have things that act as like a Pseudo and ASAP. So you're going to see that the foliations show up. But in other pieces, it's not actually going to do anything besides mix up the underlying surface in a bit of a complicated way. So you'll see that the pieces might end up swapping places. Yep. This is just a homeomorphism, but two reducible maps that end up having, that act on the surface in the same way, they'll be put in the same homotopy class. But you can just think about this as a homeomorphism of itself. So every single Pseudo and ASAP, you can write it as a product of Dane twists. But every single Dane twist, you can have an infinite number of things that lie in the same homotopy class. So you can also have the Pseudo and Nosovs technically lie in the same homotopy class, but we never actually really think about it that way. We have ways to distinguish whether two Pseudo Nosovs are homeomorphic or not. And we usually just pick a representative and stick with that guy. Does that answer your question? Okay, wonderful. Okay. Yeah. Yeah. When you take log of the stretch factor, it gives you the topological entropy. Yeah. All right, are there any other questions? Okay, so using this definition of reducible, we actually see that there's a type of Jordan form for mapping class elements. So in the same way that you can take a matrix and put it into its Jordan canonical form, so now inside the matrix, you see these other block matrices, you can actually break up a mapping class into different pieces. So this comes from the definition of reducible. So what we do is we take an element of the mapping class group and we take it up to a sufficiently high power because we want each of the subsurfaces to stay fixed. So when each subsurface is fixed, you're going to get that it splits into different pieces. You'll either get the shaded pieces, which are going to be either Pseudo and ASAP components or Dane twists. And you can actually pick out the Dane twists because the Dane twists are the objects that lie in these annular regions. So they're just neighborhoods of a curve. The other pieces that are unshaded, they're just fixed. There's nothing happening there. So the nice thing about mapping class elements is you can always think about them as having this Jordan form. So my favorite type of mapping class to think about are the Pseudo and ASAP mapping classes. The mapping classes that end up mixing the surface in the most complicated way. My favorite example of a Pseudo and ASAP map is a taffy pulling machine. So this taffy puller has 3 different rods, 1, 2, 3. And what they do is they place the taffy on the machine and they let the machine mix air into the taffy so that the taffy gets its desired texture. And as it turns out, the map that they use actually ends up being a Pseudo and ASAP map. So what we do in the study of mapping class groups is we say, okay, let's model this on the plane with some punctures. So each of these 3 points, think about them as punctures in my plane. You can also think about them as the rods of the taffy puller machine. So if you take some time to watch a taffy puller online, which you can do, what you're going to notice is that it's going to take the center rod and the rightmost rod and twist them in the counterclockwise direction. And then the next thing the taffy puller does is it takes the center rod and the leftmost rod and it twists them in the clockwise direction. So the way that we study this map in mapping class groups is we take our plane and we draw a curve on it. And now we're going to iterate our map and see what happens to the curve. So I'm going to start off by taking the centermost puncture and the rightmost puncture and twisting in the counterclockwise direction. And then I'm going to take my center puncture and my leftmost puncture and twist in the clockwise direction. Okay, that's not so bad. We see that the curve has changed, but that's not too complicated. This is still easy for us to look at. Let's do it again. So I'm going to take my centermost dot and the leftmost, or the rightmost, sorry, twist counterclockwise. Now I'm going to take the leftmost and center and twist clockwise. Oh boy, it has suddenly gotten significantly more complicated. And in fact, if I do it again, it becomes almost impossible to draw it because there's so many different strands going around each of the punctures. So what do we actually do to study this? You can really only draw a couple of them before these curves get so complicated that you can't keep track of them anymore. Well, something to notice is if you look at this curve up here and this curve down here, they have a really similar shape. Notice that there's a strand going around this puncture, and then we see 3 strands going around this puncture in a similar motion. I notice that there's a strand going around the leftmost puncture, and I see that those same 2 strands are showing up here and kind of following in the same pattern. So as it turns out, Thurston was able to show that you can redraw these curves so that you start grouping together the different curves here, and you start kind of squishing them together. And as you continue to redraw them, you can draw them as something that we call a train track. So a train track is a smoothly embedded graph into our surface. And notice that all of the branches end up lying tangentially to one another. So what you're going to notice here is that these 3 strands here now correspond to this piece here. And that'll turn into 6 down here, which we notice right there. So all you're doing is you're taking all of the strands and finding a pattern, and then you're going to encode it into this graph. Now let's notice what happens if we apply our map to the graph. So here I see my graph, and I'm going to put on 2 labels, X and Y. I only need to label 2 of the branches of the train track. And that's because here I have X, and this will turn into X over 2, Y, and this will be Y over 2. Then X plus Y form into X plus Y here. And then I have X plus Y over 2. So that's nice. I only have to keep track of 2 labels. So now when I apply my map, so when I take my center puncture and rightmost puncture and I twist counterclockwise, I get to this picture here. And now I'll twist my center puncture and leftmost puncture in the clockwise direction, and I end up here. But notice, if I do that same squishing procedure and I redraw the picture on the bottom right, I get back to the picture on the bottom left. But this is the same train track as above. The only thing that's different is that the labels have changed. So what I'm going to do is I'm going to look over on the side. I'm going to notice that here I have a y, here I have an x, and here I have another y. Does that mean that means that this branch here has to be x plus 2y? The branch that was originally labeled x is now over here, so that's equal to x plus y. So what I have is a map that takes x to x plus y and y to x plus 2y. I can encode that in a matrix. Now I have the matrix 1, 1, 1, 2. When I apply to the vector xy, I go to x plus y and x plus 2y. Thurston was able to show that the eigenvalue of that matrix corresponds to the stretch factor, and the information that you get from the eigenvectors corresponds to the two foliations on your surface, the unstable and stable foliations. And now a fun fact, the stretch factor here is equal to the golden ratio. And there's a fun reason to see why the golden ratio shows up here. Let's go back to the picture where we've actually drawn out the curve. What I'm going to do is take an arc from the center puncture and draw it downwards. So now it intersects the curve, and I'm going to count the number of times that I intersect the curve with this arc. In the first image, it intersects once. In the second image, it intersects twice. In the third, 3 times. In the fourth, 5 times. And in the fifth, 8 times. These are the first 5 sequences of the Fibonacci sequence. As it turns out, if you continue to iterate this map, you get the entire Fibonacci sequence. And it's an open problem whether you can take every single sequence and encode it with a Pseudo and ASAP map, which is a pretty interesting problem when you think about it. So this inspired a question which was posed by Fried. Which real numbers are able to arise as stretch factors lambda? And this is going to take me to the first project that I want to discuss, which is titled a construction of Pseudo and ASAP homeomorphisms. And this was a project that I worked on during my thesis. So part of this work was inspired by the question by Fried, which real numbers arise as stretch factors lambda? The work of Thurston was able to show that all stretch factors are algebraic integers with degree between 2 and 6g minus 6. So you can already take every single real number that's not algebraic. It's never going to show up as the stretch factor of a Pseudo and ASAP map. So there's 2 classical constructions of Pseudo and ASAP homeomorphisms. There's one defined by Thurston and a second defined by Penner. I'm not going to define these for you, but an important conjecture that came up in this work is that Penner conjectured that every single Pseudo and ASAP map up to a sufficiently high power should come from his construction. So that means that all stretch factors would arise as a Pseudo and ASAP mapping class from Penner's construction. Work of Shin and Strenner was able to show that not all stretch factors are able to come from Penner's construction. And what they did is they studied the algebraic properties of the maps from Penner, and they constructed some Pseudo and ASAPs that could not have those properties. So now you can ask a second question. Can all Pseudo and ASAP mapping classes come from the constructions of Thurston and Penner? And in my thesis, I was able to show that that's also not the case. So the way that the main difficulty in studying a problem like this is when I have 2 Pseudo and ASAP maps, how do I know I can tell them apart? You can't do this with a train track. You can have very many Pseudo and ASAPs with the exact same train track. So you need to do something a little more sophisticated. So what you actually do is you end up looking at the number theoretic properties associated to the stretch factor, and you try to see when those properties differ, because those are going to be invariant. Yep. Yes, but we only look at the ones whose modulus ends up being the largest, so we only look at real eigenvalues, but complex numbers will come up in a minute. All right, so the theorem that I showed is that there exists a construction of Pseudo and ASAP mapping classes which produce new Pseudonosups, which are unique from the constructions from Thurston and Penner. So the first thing that you have to do is actually make your construction. So I constructed Pseudo and ASAP maps using Dane twists around multi-curves. So here's a surface. This is a sphere with 8 punctures, where when you look at each of these 8 little cusps, those correspond to the punctures on the surface. And then I have a collection of 4 different curves on the surface. So I have 3 red curves, 1 here, 1 here, and 1 here. Notice that the domains are all disjoint. When the domains of Dane twists are disjoint, you can twist them all at the same time because then they don't interact with each other in any way. So I have a collection of red curves, a collection of blue curves, and then I have a pink curve and a green curve. What I'm going to do is I'm first going to twist the red curves in the positive direction, then the blue curves in the positive direction, the pink curve in the positive direction, and the green curve in the positive direction. And I'm able to show that this gives me a Pseudo and ASAP map. So this construction is much more extensive than this, and it goes to many other punctured spheres. But I want you to think about this particular map, because this is one of the maps that ends up being unique. So the next thing I do is I'm going to study the number theoretic properties associated to my map. The first thing that we end up studying is the trace field, which is defined to be the algebraic extension over Q of lambda plus lambda inverse. And Hubert and Lenoux were able to show that in Thurston's construction, the trace field is always totally real. Well, when I looked at the trace field of my map, it's actually not totally real. So my map isn't able to come from Thurston's construction. The next thing that we can study are the Galois conjugates of the stretch factor. Shin and Strenner were able to show that for Penner's construction, the Galois conjugates are never on the unit circle. But my map has Galois conjugates that do lie on the unit circle. So it also can't come from Penner's construction. So at this point, we have an entirely new map, an entirely new Pseudo and ASAP map. And just so you know, the question is still open. We still don't know exactly which real numbers end up arising as Pseudo and ASAP maps. And I also want to point out that Shin and Strenner actually constructed maps where all the Galois conjugates lie on the unit circle, except for the stretch factor and its inverse. So the next theme that I want to cover is this object called the curve graph. So the curve graph was defined by Harvey, and the vertices correspond to homotopy classes of essential simple closed curves on your surface. So let's go through all these words. The word simple here means that the curve is not going to self-intersect. So I was really nice, and all of the curves on my surface do not self-intersect. The next word is essential. Essential means that I'm not going to be homotopic to a point, a puncture, or a boundary component. Well, if I look at this orange curve here, notice that I can continuously deform it down to a point. So that orange curve is not essential. So there is no vertex on this side here that's going to correspond to that orange curve. The next word is that I'm going to take everything up to homotopy classes. So notice that if I look around this genus, I've drawn two curves, and I can continuously deform this curvy curve into the more smooth-looking curve. So those two curves, even though you can draw them differently on the surface, lie in the same homotopy class, and so they only get one vertex in the surface. And then I'm going to place edges between two vertices if I'm able to realize the curves disjointly on the surface. So what I mean when I say realize is if you just draw two curves on the surface, they might intersect a couple of times, but you might have these little bigons. But if you have a bigon, you can push them apart. Because again, we're taking everything up to homotopy. Of Harvey? No, I don't, but I also don't remember if he published under his first name or just first initial. I have a book, though, that cites him, that I can get you the information for it. But yeah, a cool fact about this curve graph is he actually defined it to give us a new proof of a representation of the mapping class group. So it's really neat that this is like a purely combinatorial object, and you can actually end up proving very powerful results about the mapping class group using it. So another powerful result is by Bonoff. Bonoff was able to show that the mapping class group of a surface is isomorphic to the group of automorphisms of the mapping class group, which is isomorphic to the group of automorphisms of the curve graph. So let's think a little bit about why this is true. And I want to start by looking at why is the mapping class group isomorphic to the group of automorphisms of the curve graph. So notice that there's a natural map from the mapping class group to the group of automorphisms of the curve graph. And this is because if I take two curves that are disjoint on the surface, what I'm doing is I'm applying homeomorphisms to the surface. So if two curves are disjoint, they have to be disjoint in the image. So they can't all of a sudden intersect. But that means if I have an edge in the curve graph, it's going to map to a different edge in the curve graph when I apply this homeomorphism. So that's why it's going to induce a map on the automorphisms of the curve graph. But now there's a question. Suppose that I apply an automorphism to my curve graph. Does this induce a homeomorphism of the surface? So in particular, can you use graph theoretical information to determine where each point of the surface gets mapped to when you apply this automorphism? And Ivanov was able to show that you could. Ivanov showed that for surfaces of genus at least 3, the natural map from the mapping class group to the group of automorphisms of the curve graph is in fact an isomorphism. So now let's look at the second part of this. Why is the mapping class group isomorphic to the automorphisms of the mapping class group? Well, what we can do is we can take an element of the mapping class group and it can act on itself via conjugation. So that gives us an automorphism of the mapping class group. So Ivanov was thinking, how can I show that an automorphism of the mapping class group is going to be isomorphic to the mapping class group? Well, automorphisms of the mapping class group preserve powers of Dane twists. I'm not going to go into the proof of that. That's actually a pretty great observation by Ivanov. But something to notice here is a Dane twist is really just defined based on the curve that you're twisting around. So for every Dane twist, you really just have to think about the underlying curve on a surface. But what object encodes the underlying curves on a surface? The curve graph. So he was able to show that this question about the mapping class group being isomorphic to the group of automorphisms of the mapping class group is actually just a question using the curve graph. And so this is an example that shows us that the curve graph is actually able to be used as a combinatorial tool to study the mapping class group. And a lot of really difficult questions in the study of mapping class group have been able to be reduced to a problem about the curve graph. Yeah. I don't remember exactly if you need 3. I feel like you can go down to 2. I think, yeah, I think 1. I don't know. The torus is always a problem child. We'll get into that in a minute. Yeah. Yeah, but the torus is always a problem child because if you think about the curve graph of a torus, well, every single curve is going to intersect. So it's totally disconnected, which means you can't use the regular definition. You have to start using intersection 1. So yeah, I'm always tori kind of, I have healthy amounts of skepticism towards them. Okay, but the work of Ivanov inspired a lot of mathematicians to say, okay, I have these graphs that are naturally associated to a surface. When is the group of automorphisms of these graphs isomorphic to the mapping class group? And here's a long list of researchers that ended up studying various problems of this flavor. So Ivanov made the following meta-conjecture. For any sufficiently rich graph G naturally associated to a surface S, the group of automorphisms of that graph is going to be isomorphic to the mapping class group of the surface. So this leads me into my second project, which is titled Automorphisms of the Fine Curve Graph. And this is work which is joint with Adele Long, Dan Margalit, Anna Pham, and Claudia Yao. And something I want to point out is that this project was done during the Research Experiences for Undergraduates program at Georgia Tech. So Adele, Anna, and Claudia were all undergraduates at the time of this research project. So the fine curve graph was defined by Bowden, Hensel, and Webb, and the vertices correspond to essential simple closed curves. So we've dropped the word homotopy class. So what this means is that now these 2 curves going around this genus, we have 2 vertices representing these 2 curves. So now when I say disjointness, I mean disjointness as drawn. If you draw a curve on the surface that doesn't self-intersect itself and is essential, then that is a totally kosher curve to put on this. That does mean that this curve graph is locally uncountable around every single vertex. So a question you can ask is the group of automorphisms of the fine curve graph isomorphic to the group of homeomorphisms of a surface? And the reason why we're looking at the group of homeomorphisms of a surface is because we dropped the word homotopy class in the definition. So Notice that there's once again a natural map from the group of homeomorphisms of a surface to the automorphisms of the affine curve graph. And this once again corresponds to the fact that disjoint curves have to map to disjoint curves, which means edges in the affine curve graph map to other edges in the affine curve graph. What we were able to show is that for closed surfaces of genus at least 2, that natural map is in fact an isomorphism. The group of automorphisms of the affine curve graph is isomorphic to the group of homeomorphisms of a surface. So what we know is that every homeomorphism of the affine curve graph induces an automorphism of the affine curve graph. But what we need to show is that every single automorphism of the affine curve graph induces a homeomorphism of the surface. But this is really hard. And the main difficulty here is how am I able to encode points on my surface using only graph theoretical information? So what we decided to do is we decided to look at an easier version of this graph. And what we decided to do was essentially factor through the graph. So we know we have a natural map from the group of homeomorphisms of a surface to the affine curve graph. Well, let's see if we can define a map from the affine curve graph to the extended affine curve graph. And the proof of showing that the extended affine curve graph is isomorphic to the group of homeomorphisms of a surface ends up being much easier. So the extended affine curve graph is the graph that's defined where the vertices are just simple closed curves. So our poor orange curve, this inessential guy, finally gets to be a vertex of our graph. And once again, edges correspond to disjointness. So Verberne and Margalit studied the extended affine curve graph, and they were able to show that there's this correspondence between the topology of the surface and the graph theoretical information in the affine curve graph. So they were able to show that you can define these things that they call convergent sequences. So we say that a sequence of curves converges to a point X if for every neighborhood of the point X, it contains all but finitely many of the curves in the sequence. So this ends up being in one-to-one correspondence with the following two pieces of graph theoretical information. So the first piece says that there exists a vertex A that intersects the tail of CI. So remember, every vertex corresponds to a curve on our graph, on a curve on our surface. So if we imagine a curve on the surface, what we mean when we say intersects the tail, it intersects all but finitely many of the curves in the sequence. So what that means is that when I look at my graph and I look at my vertex A, it can only have finitely many edges between the curves CI in the sequence. The second piece says if A and B are distinct vertices that intersect the tail of CI, then they must also intersect. The reason why they have to intersect is if you're going to intersect all but finitely many of the curves in the sequence, and you're a different curve on the surface, you're forced to pass through the point X that the sequence is converging down to. So what this means in the graph is now I have A, I have B. Both of them can only have finitely many edges with the curves CI, and there cannot be an edge between A and B. You can pick this out in the graph. Better yet, if you have that graph theoretical information and you do an automorphism of the graph, that information gets preserved. So now I have a convergent sequence mapped to a different convergent sequence. But the convergent sequences give points on my surface. Now I have a point on the surface gets mapped to a different point on the surface. So using that, Verberne and Margalit were able to show that for any surface without boundary, the natural map from the group of homeomorphisms of a surface, the automorphisms of the extended affine curve graph, is in fact an isomorphism. So now how do we go from this easier version to the hard version? Well, what we're going to do is construct a homomorphism from the automorphisms of the affine curve graph to the automorphisms of the extended affine curve graph. And we do this by defining something that we like to call a bygone pair. So on this piece of a surface here, there's two curves, the red curve and the blue curve. So the red curve and the blue curve are exactly the same on this interval here. I know it doesn't look like it in the picture, but they are exactly the same. Outside of that interval, they're allowed to differ and do whatever they want. But notice, if I take out my scissors and I cut along both of those curves, I get that a piece of the surface is still connected, and then I get a disk. But the boundary of that disk ends up encoding an inessential curve on the surface. So I'm able to use essential curves to define inessential curves. And luckily for us, we were able to show that automorphisms of the fine curve graph end up preserving these bygone pairs. So what we have is that if we do an automorphism of our graph and we have a bygone pair here, then we're going to have a bygone pair in the image. So now I have that an inessential curve is mapped to an inessential curve. So I'm able to define a homomorphism from the automorphisms of the fine curve graph to the automorphisms of the extended fine curve graph. So that's how we end up showing, once we've composed all of these maps together, that for closed surfaces of genus at least 2, the natural map from the group of homeomorphisms of a surface to the automorphisms of the fine curve graph is in fact an isomorphism. So the final theme I want to discuss today is the theme of hyperbolic graphs, and in particular, groups acting on hyperbolic graphs. So the first thing I have to define is a thin triangles condition. So here I have a triangle, and notice that around 2 of the edges, I've drawn this delta neighborhood right here. So we say that a triangle is delta thin if you draw delta neighborhoods around 2 of the edges, then the third edge is still contained inside of these 2 delta neighborhoods. We say that a geodesic metric space is Gromov hyperbolic if it satisfies the thin triangles condition. So what that means is if I have a metric space and I pick 3 points, and I look at a geodesic triangle, that triangle must be delta thin. So a nice fact about the curve graph, which was proven by Mazur-Minsky, is that the curve graph is Gromov hyperbolic. So the mapping class group, what we saw earlier, is that it acts on the curve graph. So the mapping class group acts on a Gromov hyperbolic space. Yep. Yeah, genus 2. Yeah, for the torus, yeah, tori are a little problem child in mapping class groups. Yep. Yeah, every edge is equal to 1. Yeah, yeah, don't complicate things. All right, so our group acts on a Gromov hyperbolic space, but something I want to point out is that our group is not hyperbolic. If you take 2 disjoint curves on the surface and you do Dane twists around them, you create a flat because they end up being disjoint domains. And so you can just create an embedding of Z2 sitting inside the mapping class group. Yeah. So we have hyperbolic directions. Those are called the Pseudo and ASAP directions, but we also have these flats sitting inside of it. So a non-hyperbolic group does act on a hyperbolic space. What do you mean by that?
I mean, the thing that you are just hyperbolic direction.
Yeah.
So the other classes.
Yeah, they mainly correspond to flats. The one thing you have to watch out for, no, yeah, they're 100% flats. Yeah, you're right. Okay. So in the work of Mazur-Minsky, they also studied the action of the mapping class group on the curve graph. And what they were able to find is there's type of Nielsen Thurston classification based on which element you're looking at and how it acts on the curve graph. So you're able to show that if you take an element of the mapping class group, it's going to act on the curve graph in one of 2 ways. It'll either act elliptically. What this means is if you look at your element acting on the curve graph, every orbit stays bounded. We know this is true if you're finite order because eventually every curve maps back to itself. And it's true for reducibles because remember, you're going to have this collection of disjoint curves, which corresponds to a simplex in the curve graph. And those curves have to be mapped back to the same set. So you just get a rotation of your simplex. So that also tells you that the action there is going to be bounded. The final type are the hyperbolic mapping classes. So these are the ones that translate along an axis. And these correspond specifically to the Pseudo and ASAP mapping classes. And the way Mazur-Minsky was able to show this is that if you take a curve on the surface and you iterate it by a Pseudo and ASAP, the distance between the curve and the iterate is going to be bounded below by the number of times you've iterated the map. What that also tells us is that this curve graph is going to be infinite diameter. And in order to find hyperbolic actions on your graph, you have to have an infinite diameter graph. So what if we try and define a curve graph for infinite type surfaces? So remember, these are the surfaces that have an infinite amount of topology. So if I take two curves on the surface, these are compact, they can only take up a finite amount of room on my surface. So I have an infinite amount of room to draw a third curve that's going to be disjoint. This tells me that my graph is going to have diameter equal to 2. But then I can't pick out these nice actions that the mapping class group has on the graph. So this isn't actually a good model to look at if I want to use a curve graph to help me study the mapping class group of an infinite type surface. So can we find a curve graph for infinite type surfaces that satisfy the criteria that we want? Delta hyperbolic, connected, infinite diameter. Those are the big ones. There's been a lot of research done trying to find graphs that fit all of this criteria, but we have two big issues. Either we find a great graph, it only works for a couple of different surfaces, so that ends up being a bit of a bummer. Or we end up getting graphs that apply to a lot of different surfaces, but it's missing one or two of the properties that we really, really want. So this is going to lead me into my third project, which is titled the Grand Arc Graph. And this was done in joint work with Asaf Barnatan, who's currently a postdoc at Brandeis. So I really quickly want to go through why we would study infinite type surfaces in the first place, because this is a bit of a jump from looking at finite type things. And the first thing is there's a pretty big connection to complex dynamics. So if you take the family of polynomials z squared plus c, you're able to define a Julia set for each parameter c. So this is a Julia set when c is equal to 0.285 plus 0.01i. And notice this is totally disconnected. It's Cantor dust. But I can end up varying the parameter c, and I can vary the parameter c so that it comes back to itself, which means I see this Cantor dust moving around the plane and eventually comes back to itself. The complement of the Cantor dust is a plane with a Cantor set of punctures removed. That's an infinite type surface. So complex dynamicists are interested in infinite type surfaces because they correspond to homeomorphisms of infinite type surfaces in certain cases. I'm going to skip over this for the sake of time. And the first thing I want to do when we discuss infinite type surfaces is define the case of an end. So an end is a way of exiting every compact set of the surface. So here I have a surface and I have infinite genus going off to one direction and infinite genus in the other direction. We're going to see if it'll let me draw today. And it's not. So notice what I can do is I can take a surface of genus 2 with two boundary components here and here. That's a compact surface sitting inside. But now I can take a bigger one. So I can take a boundary component here and here. So now I have a surface of genus 4 with two boundary components. So I can have this nested sequence of compact surfaces, and I can cover the entire infinite type surface with this. When I look at the complement, I'm going to have two pieces all the way at infinity. And these are going to be the two ends of the surface for this case. Another example, oh dear. I don't know what just happened. Sorry, it seems like my computer has just decided to freeze. I think I have to try turning it off because it's just frozen. I'm so sorry. Yeah, the unfortunate thing is I have to draw a lot, so I don't think we'll actually get to it. Okay. Sorry, I don't know how to fix this right now. Let's see. We could. I emailed it to myself. Yeah, I think my computer has decided that right now is the perfect moment to give up after a long pandemic. Oh, we might be in luck. I think my talk is over time now. Okay.
Like,
All right. Should we see if this one will decide to turn on since it's almost there? I mean, it did it last night, so I really hope not. But I guess it's Windows, so who knows? It's literally like, oh, I have a meeting right now. No, I don't. Aha, okay, it's working. We are a success. All right. Yeah, I think it was like, you want to write today? Absolutely not. It knows it's a tablet, but apparently not all the time. Okay, so this second surface here, think about a binary rooted tree. If you look at the leaves of a binary rooted tree, that's a Cantor set. All right, now blow it up like it's a balloon. That gives you this surface here. And so every single leaf of the tree is now a puncture. So you can also think about this as a sphere with a Cantor set removed. And we like to call this guy the Cantor tree. But don't get too comfortable. Things get really weird really fast. So here we have a Cantor tree. We decided at every fork in the road, we're going to put a genus there. But then we're also going to glue on another end over here with infinitely many genus. So ends that have an infinite amount of genus, we call those ends accumulated by genus. Everything else we call a planar end. So work of Mann and Raffi was able to show that there exists equivalence classes of ends. And so what Assaf and I thought is we're going to define a graph using bi-infinite arcs and this equivalence class definition. So here's an example of a surface. I have a regular Cantor set down here, so a Cantor tree. Now I have a Cantor tree here with a puncture at every fork in the road. And the reason why these punctures are different than the punctures down here is if you take a sphere with a Cantor set removed and you take any neighborhood of the ends, you always get back a Cantor set. So they're not isolated. But notice that I can just take a neighborhood here and it is isolated. So those are going to be isolated. And therefore, it's in a different equivalence class than the Cantor set. But now I have a Cantor tree with genus, which means all of these ends are accumulated by genus. All the other ends are planar. So that's its own equivalence class. And then, of course, the Cantor tree is also in its own equivalence class. So now what we're going to do is take bi-infinite arcs. And so what that means is that every arc is eventually not going to leave a neighborhood of one of the ends. And what we do is we're going to take these arcs and they're going to start in one equivalence class, travel around the surface, and end up in a different equivalence class. What we do is we take isotope classes of what we like to call, so these bi-infinite arcs that start in one equivalence class and another, we call them grand arcs. We take them up to isotopy. And when they're disjoint, we're going to place an edge between them in the graph. Assaf and I were able to show that for a very large collection of surfaces, the grand arc graph is connected, hyperbolic, has infinite diameter, and the mapping class group acts continuously on the visual boundary. I don't want to talk about the last part. The reason why we care about continuity on the boundary is so that we can kind of understand the action in a nice way, so that it's not totally discontinuous and does something completely out of control. So the proof that we do ends up utilizing the work of Hensel, Perchitsky, and Webb, where they define unicorn paths on finite type surfaces as a way to give a new proof of the hyperbolicity of the curve graph. So here we have a surface of genus 3 with two boundary components, and we have two arcs. Here's one A and the second one B. What they did is they said, notice there's two places where they intersect at the point P1 and the point P2. And they define a starting point of the curve A, which they're going to call alpha, and an endpoint of the arc B, which they call beta. The first unicorn arc, you're going to start at your point alpha, travel along A until you hit P1, and then you're going to travel along B until you hit beta. Your second unicorn arc, you start at alpha, you travel along A until you hit P2, and then you travel along B until you hit beta. Notice, if I end up taking my second unicorn arc and I draw it slightly below my first unicorn arc, they're disjoint, which means the first unicorn arc and the second unicorn arc have disjoint representatives. What that means is if I'm looking at arc graphs, consecutive unicorn arcs are able to be realized disjointly. So now I can build a path between them if I'm looking at a graph defined using arcs. But their work is done in the finite type setting. We're looking at infinite type surfaces. But fortunately for us, Benoni, Gaswell, and Maclay were able to generalize unicorn paths for infinite type surfaces. And so thankfully for us, these unicorn paths allow us to show that our graph is connected. And this is because we can use unicorns, so that for any two arcs in our graph, we can find a path between them. And it also helps us to show hyperbolicity by following a similar path to how Hensel-Perchitsky and Webb use unicorn arcs to prove a new way that the curve graph is delta hyperbolic. So I want to end this talk with some open problems that still exist in the study of mapping class groups. The first question is, what is the smallest stretch factor on a genus G surface? Chris Leininger was able to give the result for exactly one surface, which is the surface of genus 2, and the smallest possible stretch factor is equal to Lamer's number. But it's still open for every other surface. A second question is there some type of a Bonoff meta-conjecture for the group of homeomorphisms of a surface? So am I able to find a collection of graphs so that the automorphism group of these graphs is isomorphic to the group of homeomorphisms of a surface? A third question is there a Nielsen Thurston classification for infinite type surfaces? And you might think to yourself, Yvon, why wouldn't it just be periodic, reducible, and Pseudo and ASAP? We genuinely don't know what Pseudo and ASAP mapping classes look like on an infinite type surface. It's really non-trivial to try and figure out what that would look like in an infinite type setting. And what does that mean for a stretch factor? We don't know yet. So it's still a completely open question about whether or not there's Pseudo and ASAP, and what does that mean? A final question is, can we characterize the action of the mapping class group on the grand arc graph? So a good starting point is we know that there's going to be, again, elliptics, and we know that there's going to be hyperbolics. There's a third type of action that you can study on graphs called parabolic. We don't know whether or not parabolics can show up in this setting. And a really interesting result is the fine curve graph is able to be acted on by the group of diffeomorphisms of a surface. And Hensel, Perchitsky, Webb, and then I believe Mann and Milton were able to show that you can define a parabolic action of the group of diffeomorphisms of a torus with one puncture on the fine curve graph, which is wild. And this is the end of my talk. Thank you so much for your time.
Any questions or comments?
So what if you some structure?
Which problem? Okay. All right. So one example that I know of that kind of gives you an understanding of how different they are. Look at the fine curve graph. And now instead of looking at just essential. If you turn the curves into smooth curves, you look at the smooth version of the fine curve graph, the natural surface that it should be isomorphic to is the group of diffeomorphisms of a surface. We were, not us, but Wolf and I believe LaRue were able to show that it's actually going to be isomorphic to something bigger than diffeo. And we don't know what that group is, because I don't know what group is bigger than diffeo that would make sense for that graph to be the right graph to be isomorphic to it. So the natural generalization of this fine arc graph for Diffeo ends up not being Diffeo at all. And we actually have no good understanding of which graph should be isomorphic to Diffeo, since the only good option we had turned out to be way bigger. So it ends up being a lot different if you're looking at smooth curves and smooth surfaces.
So these are for
Yeah.
It's a retraction,
Mhm.
but it's a question of lifting smooth and smooth one. Obviously.
Yeah.
But
Yeah.
the thing is, it's being
Construction won't lift.
Mhm.
measured.
Yeah.
So, surface is non-oriented. Just look.
Sometimes you end up doing a double cover and going up, but then you run into the case. So I forget what they're called. What are they called? It's when you smoothly embed a Mobius curve into the surface. You kind of thicken it and you glue it on. Is that called a handle? No, sorry, I forget what it's called. Cross cap. There we go. If you have a surface, it doesn't always work to look at the double cover. So a lot of us just look at orientation preserving. So there's a lot of results that we have in the orientation preserving case that we don't have in the case where you have orientation reserving or non-orientable surfaces. So there is a lot of work doing that. Sometimes it's as easy as kind of just lifting to the double cover, but it's my understanding that that's not always the case.
Other remark. Oh, I understand. That's fine.
Mhm.
You can't start this way. And that reconstruct.
Yeah.
So I think that is another that isomorphism as abstract and
Oh,
so
I think you're right.
and also that some area preserve are sent.
Oh, yeah, that's also a good point. I need to write that one down.
There are some and problems all those would
So if you just give me a curve on the surface, are you asking me to just check whether it's I think for homotopy, if you're separating, isn't that if you're looking at oh no, that's homology. So if you're looking at homology with z coefficients and separating curves are equal to 0 there. Yeah, we usually just cut along the curves, but we usually work with them a little more abstractly. And so the nice thing is we have something called the change of coordinates principle, which tells you that for any non-separating curve, no matter how complicated it is, you can map it to any other non-separating curve. So for us, we usually only work with the more basic non-separating curves on the surface, because then you can just hit it with a Pseudo and ASAF or with any other elements of the mapping class group and get the rest. So we usually start from the curves that we like and move up to the curves that we don't like rather than working backwards. But that's not a great answer to your question, but we usually just end up saying, we usually just simplify down.
any result about
I don't think so. I know that for big mapping class groups, they were able to show that the curve graph defined for, so the diameter 2 graph that's going to have that the automorphisms of the graph is still equal to the mapping class group of that surface. But I don't think we know anything about contractibility. In fact, we don't even know for the fine, yeah, we don't even know for the fine curve graph if that's contractible. We don't know that either. So yeah, another open question in case you want to prove that the fine curve graph is contractible. I personally don't know how to do it.
Question? Okay, maybe I'll ask a question myself. So obviously, mapping class group very simple objects.
Mhm.
You know, structures. But I just think not really like absolute L1 group, for example.
There's outer space.
Yeah,
So they look, so outer space and the mapping class group are related in a way. And I'm trying to remember what it is. So if you look at the fund, yeah. So outer space, you're looking at the outer automorphisms of the fundamental group. And then she defines a space called outer space that that group acts on. There is a relationship between the two, and I'm blanking on it now, but I think it has to do that if you look at the fundamental group of a surface of genus G, they're related that way somehow, because outer space takes the group of outer automorphisms of a fundamental group, and then that group acts on outer space. So I think. Mhm. I don't think, sorry, can you repeat your question?
That acts on. So that will.
Yeah, I don't know the answer to your question.
Other questions or comments? Okay, so let's thank Yvon.
Thank you.